Okay, so this is the second video, the follow-up on the what was that? The multi-sig cold wallet transaction using Frost on Ycash, or Sighash would be the same probably. So before we actually go into the signing and the real part of creating the finalized transaction. So we covered the creation of the shared key, the multi-sig key. Obviously, the next part should be signing a transaction. Before we go there, though, I think it's good to review how a transaction is formed when it's only a single signature. So the case that is done currently by the node. So normally what you will have, right, and that's what the core wallet does in Y wallet, is that you save a transaction that has all the information needed, inputs and outputs, the spends and the outputs, in order to form the transaction using Libra's Ycash. So we have an example of that in this test. Let's go through it very quickly. Because basically with the multi-sig, we're not going to be able to do that in one go. Obviously, there are multiple people involved, and they don't have access to the same information. So that's there will be files exchange, and the process of generating the transaction is going to be broken down into several parts. So the first part is going to be the calculation of the signature hash. So in general, when you do a transaction, you have to sign the inputs, the spends, and the signature that you create is you sign a message. So the message itself is the transaction without the signatures, of course, otherwise it would be an infinite loop. So the transaction is formed without the signatures. So by putting all the inputs, all the outputs, writing everything out, and then it's hashed, and the result is going to be your message that you sign. So what we do here is that we stop there. We create the transaction, so that includes creating the ZK proof. So everything is created except for the signatures, so that we can calculate the SIG hash. So this is the purpose of this function here. So this one, we have access to our nullifier key. So if you going back from the previous video, we were saying that in a normal spending key, in a normal extended spending key, you will have both the authorization key and the nullifier key. We don't have the authentication key in this case because we are splitting into multiple signatures, but we do have the nullifier key. So that value here is what was reported by running the DKG. At the end of the DKG, we write that nullifier key. So that's the same key that we have here. And then we get and pass that transaction file from Y wallet. So you go to Y wallet, you input the destination address, you fill the spend and the send as it was a normal account, but it knows that it doesn't have the secret key. So when you press send, it will approve. Instead of signing and sending the transaction, it will actually offer to save it as a file. So that's the file that I have then emailed to myself, and this is this file. So we parse that file. If you want to take a look, it's just a JSON file, code that has all the inputs, all the outputs, where the chain should go, and the amount and stuff like that. Right? So once you have that, then we call this function build transaction data. So the main trick here is, and this is the only change that was turned out to be a little bit of work, is to make sure that we can pass the RNG and to all the functions in LibreOS Ycash. So 99% of them actually take the random number generator as an input. So by doing that, the trick that we're doing is that we are using a reseedable RNG. So even though the sequence is pseudo-random, because we are going to reseed with the same value, the next time we're running the build transaction data, we're going to get exactly the same result. And that's important because it's part of the transaction, in particular the ZK snark proof has a random component to it. So without that, locking down basically the seed of the RNG, every time we build the transaction, we would have a different output, different bytes, and that's not acceptable. It's not possible to. It won't work out in our case because we would create a transaction, get a Sighash out of the content, then sign that, and when we go back to create the full transaction, then the transaction will be different. Right. So that's the one major work here. Lock down the transaction generator, the transaction builder with the RNG. Okay, so after that, the output of this function is going to return a couple of things, three things. The transaction data is like most of the stuff will be there, so everything, the spend description will be generated, ZK proof generated. This context here is something you would need to finalize the transaction. So we need to have that to create the binding signature. And alpha is a set of scalars which are also randomly generated. That's because when you sign, we don't sign actually on the public key. On your normal public key, there's a randomization element that was introduced in Ycash. So that even though you could be reusing the same public key multiple times, on the blockchain it will look different. So we need to know that these values are going to affect the signature. So once again, this function, if you run it a second time, you will have exactly the same result, provided that you seeded the cha-cha RNG with the same value, which I seed at 0 here. So in a real case, what you would do is you would take the transaction bytes, you would hash it, and use that as a seed of the RNG, so that it would be deterministic, but it would not be always the same sequence, obviously. Okay, so the output would be a Sighash, right? Then we stop here for to simulate the case of a multi-signature. But if it was a single signature, what you would do afterwards is actually called sign Sighash, which this time takes the secret key. So this is your authorization signing key, secret key. This Sighash here is the value that was printed out on the previous step, and also the alpha this alpha here, this value here is what was printed by the alpha over there. So in more complicated case, you would have more than one alpha because the transaction has more than one spending nodes. You would have as multiple one alpha per spending node per input, basically. But in the case I have, there turns out to be only one input. So then you would sign that input, and that gives you one signature, right? Using sign one. And finally, the final step is recreate the transaction again. So again, if you were doing that in online or only one person, these all three steps will be one after the other in the same function. So you don't have to recreate the same state as before. But since we are going to do with multiple participants, the transaction has to be rebuilt on each side. Basically, we're serializing the transaction between parties here. So we rebuild the transaction as it was before, and because the RNG is reset to the same value, the result will be exactly the same. So the Sighash here will be the same as the Sighash we calculated before. And now we add the signatures. So actually in our case it's only one signature, but the function accepts multiple signature, of course, to be more generic. And then that's it. Our transaction is finalized, and we can write it as a binary file. So that file here, the TX row, is then saved to the phone, so either by email or by USB drive. And we use a function broadcast transaction to send that transaction out. All right. So that's the case. We are pretty much going to use the same mechanism with the multi-sig, except that part here where we sign the Sighash, instead of signing with one person, we're going to create a signature with two parties, because it's a 2 out of 3 signature. All right, so next video I'm going to show how to do that part, the sign Sighash, but with a threshold signature to 2 out of 3, knowing that the rest is actually the same. The generation of the transaction, unsigned transaction Sighash, and the broadcasting, the finalization and the broadcasting of the transaction is the same. All right, that's it for today.